Hi, in this video, we want to take a look at geoadditive models when we're analyzing a real data. Now, remember, a real data is the situation where I have data for regions such as neighborhoods, counties, states, countries, etc. What we're going to do, we're going to take a look at using this, using geoadditive models in the context of disease mapping. Now, what we're going to do, we're going to work through an example from Applied Spatial Data Analysis with R, Chapter 10. Here are the names of the authors. Here is the textbook's website, and you can download this book for free through the UCF Library's webpage. All right, so let's get started on this. All right, so geoadditive models. The best description of these is just going to be say splines. All right, so what we're doing splines, and we're taking our data, and I want to fit a smooth curve to model what's going on. Now, this is kind of, you can think of this as an extension of regression. That'll work out for the right way to think about it. And so what specifically, we're going to be using penalized splines. So when you see the P, it means penalized. And that's to help prevent us from overfitting. All right, so the package that we're going to use is the R2 Bayes X package. So we're taking the approach of Bayesian statistics to knock this out for us very nicely. And the big heavy hitter in this package is the Bayes X function. And so what we're going to do, we're going to use this function to fit our geoadditive model. All right, so in the past few videos on the disease modeling videos, we've been talking about SIDS, specifically in North Carolina. All right, well, what we're going to do, we're going to say that our observed count of SIDS by county, so our real regions are going to be counties, and we're going to apply a smoothing to our data. So we have each county, we have the SIDS observed data, and we're going to use the fraction of non-white births in each county, and we're going to do a penalized spline, and we're saying to put 10 knots into our spline. Now, this will be a geoadditive model, and so we're going to be able to get a modeled value for each county. Now, we're going to apply an offset of the expected number of SIDS. Got count data, so I'm going to use Bayesian, similar to generalized linear models, Bayesian regression. And to be able to execute this, what we're going to do is I'm going to have a data frame pulled from my spatial polygons data frame. Now, you'll notice that when I do this, there is nothing in here indicating the spatial aspect of it. So this point of view would work with any type of modeling, and I'm actually losing the spatial components. All right, so what we're going to do, we're going to fit a P-spline based on the tensor product of a one-dimensional P-spline with a two-dimensional first-order random walk penalty, and that's how I'm going to set up the parameters for the spline. All right, so here, this is the actual execution of the model. When I do this, on this part, you notice I've got coordinates, and I've got coordinates. And here I've got latitude and longitude include. So for this model, you'll notice that we're able to we're using latitude and longitude. Let's compare that up here. In this part, we're only considering the fraction of non-white births in the county, but we don't have any coordinates at all. This is just honestly is a regular model. Here, to incorporate the spatial aspects, I'm including latitude and longitude. Now, you'll notice that I dropped the fraction of non-white births from this model here. Which one's better? Well, let's take a look. Let's see what happens. All right, so let's go ahead and fit our penalized spline model. And so here we have our fraction of non-white births, and this is plotting the smooth portion of that fraction. And so you can see, we have going from 0 to 1 for the fraction, and it's getting rescaled in a smoothing manner from -1 to 1. Now let's go ahead and plot our two-dimensional with a random walk model that's using a tensor product. And now we get kind of a weird representation of North Carolina, but here, the main thing we want to see, the thing that should pop out of this, is that in the northeast corner, we see more red. In the southern east corner, we see more red. And in the northwest corner, we see more blue. And then we have something kind of in the middle. So this is showing us, greater modeled risk of SIDS. All right, now we have a ton of different visualizations that we could run on this. We have all of these that we could go with. So 1, 2, 3, 4, 5, 6, 7, 8, 9 different plots that we can run when I want to do my visualizations to get diagnostics on my model. All right, well, how we invoke this is that we use the which parameter inside the plot function, just like with regular LM linear models. Now, also, I have the option of putting in 1, 2, 3, 4, 5, and so on. Now, these are not in the correct numeric order because I was having code problems. This one I grabbed from the middle somewhere. I shuffled the order to deal with some coding errors I was getting with. But an option I would also have is to put like 1 through 8, 1:8 for my plot to be able to see stuff. And what we're going to do, we're just going to do the penalized splines that's using the fraction of non-white births. So this plot we've already seen. And so this is giving us the Monte Carlo Markov chain iteration information. So this is regarding the Monte Carlo Markov chain. So this looks like things have stabilized for me, so we can actually use it and trust it. Now here's the histogram and the density. And now this is for the term in the model of the smoothing part. So we can see most of the time it's just a little bit greater than 0. So, maybe 2 or 3 is what's typical. Yeah, but it's definitely skewed right. Now, when I look at the QQ plots, I can see that I do not have normal residuals for sure. This is not normally distributed 100%. I'm absolutely sure of that. Now, that's only a concern really if I need to have a distribution for an inference. I don't need the normal distribution for residuals unless I want to run specific hypothesis tests that invoke the normal distribution, such as typically with ANOVA. Now here we're looking at the fitted value versus residuals. So now here, I don't like what I see. I see a curve for the fitted value with residuals going along that curve. That shows me that there's probably a problem with my model. So I would definitely want to dig in deeper before I would launch this. And scale location along the fitted values, I'm seeing a curve here. And now we can look at the time series plot to look at the autocorrelation. And here, we see kind of a few poking up here and there. We see a good drop right after the beginning. We will always have a autocorrelation at 1, then it drops off. And now here, I wasn't able to get this to look right on my machine, but here we have, you know, the penalties being displayed. Doesn't look right on my machine, honestly. I couldn't get it to work. Now, the R2 BaseX package has some other functions to help us analyze and take a look at our model. First one, of course, is going to be the summary function. And it, you know, gives us our code for how we got it. Gives us the parametric coefficients, nice, you know, basic statistics, and smoothing term variance. And also, it tells us about the our sample size, our burn-in, our thinning, and our number of iterations. Now, something that I'm going to show you in a moment that I haven't quite shown you yet is that there's a function that will give me a collection of function calls to pull out the information very nicely, ones that are going to be used that you would want more often than others. So here, this plot, which I got from the function in the package, which I'll show that function in a moment, it gives me this. And once again, I get to see the autocorrelation. Now here we're taking a look at the smoothing of the fraction of non-white births by the fraction of non-white births. We've already seen that. Here is our samples of the intercepts. Looks like it's stabilized to me. Here's the intercepts autocorrelation. This looks very good for that purpose. Once again, the coefficient samples just doesn't work out for us. You know, the information is there, the information is good, but I can't get it out of the, I can't get it to display correctly. Here we can take a look at the maximum autocorrelation. And of course, if I'm looking at the maximum, I'm expecting more spikes. Here we're looking at the variance sampling diagnostics. And here's autocorrelation again. All right, now how did I get all those plots? So here, the get script function from the package gives me all of these and a little bit more. So you'll notice that the summary that I already called and the plots that we just took a look at all are there for us to analyze our Monte Carlo Markov chain model to check to see if things are looking good. Now here it gives us, you know, a way to save as an RDA object the model, and here it gives us a way to load that RDA object afterwards. Now there's some other things to help us out with analyzing what's going on. So we have the runtime, so BaseX runtime. And we can get the program files. So this just gives us information on what's going on. We'll use the predict function, just like in the rest of R, to get predicted values, and it gives us the mu. We can get the fitted values, which we're getting the same mu, but the difference, so when I'm using predict, it's predicting values on observed data. When I'm using fitted, because this is part of the data set that was used to build the actual model, we get more to it. We get the same mu, but we also get the linear prediction aspect. We can also get samples out of there, just like with any other Monte Carlo Markov chain. And the next thing that we get from the BaseX log, R2 BaseX package is the log file. And now here, this gives us, like a lot of outputs. Gives us a lot of stuff. If we want to go in, start digging in, you can see number of iterations, burn-in period, thinning parameter. Here we've got our response, distribution. And we, if we want to go back and read and start digging into it. So here, these hyper priors are selected to have very little, to not bias our models, to be very vague, honestly. And here we get, information about our fixed effects. Here we get information for the fraction of non-white births. That's on the estimate itself. Here is on the variance of the estimate. And we can just keep on scrolling through and just digging in if we need this. The information on the predicted values. Now here's the DIC. So think of this as like AIC, where we're taking a look at the log likelihood of the model and a penalty term. So the smaller it is, the more negative, the better the fit. And I can use this to compare multiple models. Now we get to our fixed effects. And we see that we have a mean of 0.1. And we just keep on digging in and analyzing the heck out of this. Now, let's say that we were interested in a different type of model. So in the examples, we use PS and we use TE. PS is for P-spline with first or second order difference penalty. TE is for using a tensor product of a P-spline with a random walk. We have plenty of other options, and on my machine, all of these ran. So here we can go with 0-degree P-splines if we choose seasonal effects of a time scale. I already talked about these two. We can do kriging. We can do geokriging, stationary Gaussian random fields. We can do geosplines based on 2-dimensional P-splines. We can do Markov random fields, nonlinear baseline effects, and a hazard regression. Now, this one factor is specific for factors. And we can also do ridge, lasso, and it's going to be negative inverse gamma mixed effects. So we have shrinkage for special effects. So here, if the coefficients get big, we apply a penalty to help keep the coefficients down in size to prevent overfitting. And then RE is for Gaussian random effects. And just to make sure that these ran, I played around, and what I did, I created a list of all the different types of models within the smoothing parameter. All right, well, that's all I've got for you. Take care and goodbye.